Last time we discussed block arithmetic, but a more general name for that would be modular arithmetic or congruence. Do you remember how we defined congruence last time? When do we say two integers are congruent modulo n? Anyone? Yes, Maritel?
Integers a and b are congruent modulo n if n divides the difference a minus b.
Okay, that's correct. So, in our example last time, we made use of the clock. And we talked about the numbers 1 to 12. And remember, we said we'll replace 12 by 0. And every time we reach 12, we start from 0 again. Okay. So, to what number is 18 congruent in modulo 12? Yes, Ronnie?
18 is congruent to 6.
Is 18 congruent to 6 modulo 12? Let's see. Using our definition, 18 is our A, 6 is our B, and 12 is our N. By the way, there's another name for N. Can you tell me how shall we call N? I think I mentioned it last time. It starts with the letter M. Anyone? Letter M? Starts with the letter. How shall we call N? Starts with the letter M and ends in S. You remember? Yes, Jay?
N is also called modulus.
Yes, that's correct. Modulus. Okay. Oh, modulus. All right. So let's check. Using the definition, 18 is congruent to 6 modulo 12 if and only if the modulus 12 divides the difference a minus b, which is 18 minus 6, right? So, does 12 divide 18? What's 18 minus 6? 12. Does 12 divide 12?
Yes.
Yes. Okay, so therefore, we can conclude that 18 is congruent to 6 modulo 12. Okay. Actually, in the clock, when we reach 1800 hours, it's equivalent to 6 p.m. Okay? Can you give me a number from 1 to 12? 1 to 11. Abigail?
7.
7. Okay. Let's check. Is 18 congruent to 7 modulo 12? What do you think?
It's not.
It's not? Okay, let's check. Does 12 divide the difference 18 minus 7? Meaning, does 12 divide, what's 18 minus 7? 11. Does 12 divide 11? No. Therefore, we say that 18 is not congruent to 7 modulo 12. And how do we denote that? What symbol do we use? Yes, JR, you were doing that? So, we need to put a slash there. That means 18 is not congruent to 7 modulo 12. Just like in equality sign, we use a slash to denote inequality. Alright. Can you give me your favorite two-digit number? What's your favorite two-digit number? Maritel.
5 and 7.
No, one number only, but there has to be two digits.
21.
Maritel has 21. And your boyfriend, friend JR, can you give me another two-digit number?
Number 14.
14, okay. Let's see if their numbers are congruent. Modulo, say 9. Okay. Is 21 congruent to 14 modulo 9? What do we do? What do we do? We can use the definition and check whether 9 divides the difference 21 minus 14. But there's another way. Can we reduce these numbers to simpler numbers? and see if they are equal. Okay, so remember our modulus is 9. Our n is 9. When we divide by 9, what are the possible remainders? What are the possible remainders when we divide by 9? Can we get 0? Okay, in that case, the number is exactly divisible by 9. Okay, so it can be 0. What else? It can be 1, 2, 3, 4, up to? Why not 9? Okay, so this is actually the set of remainders for division by 9. And this make up our set Z9. Remember that? Okay. Again, there's another term for remainder, the word remainder. And it starts with the letter R. Can you guess? We are, in effect, reducing these numbers to smaller numbers. It starts with the letter R. Anyone? Any wild guess? Ends in E. Another name for remainder? It's actually what remains. What remains when you divide by 9? Okay? When we speak of solutions, we speak of, yes, I heard it. Yes, Roxanne? Yes, residue. Okay. All right. So let's see. If I divide 21 by 9, what residue will I get? What remainder will I get? 3. So if I divide 21 by 9, I'll get something like what? 2 remainder 3. How about 14? If I divide 14 by 9, what will I get? 1 remainder 5. Is 3 equal to 5? No. So that means these two are not congruent. Modulo 9. I'm sorry, but the numbers of Maritel and JR are not congruent. Oh, okay. How about, let's see. Abigail, what's your favorite 2-digit number? 13. Wow, lucky number, huh? Okay. Who's your friend this time? May I ask? I cannot see your name. Migs. Okay, Migs. Can you give me a number that is congruent to 13 modulo 5?
23.
23. Let's see. How did you get 23? Okay. Let's see. What's the remainder when you divide 13 by 5? You get 3. When you divide 23 by 5, you get 3. And is 3 equal to 3?
Yes.
Okay, therefore, 13 and 23 are congruent. Modulo 5. What else did we do last time? We had an activity last time, right? Remember?
Yes.
Okay. You were grouped into 3. But you worked on the same table. You were asked to do the addition table for Z4, if I remember it right. And to each element of Z4, we assigned a specific design. And the first group was actually asked to do the translation. So this was their work. The second group was asked to do the rotation. And the third was asked to do the reflection. So we realized that we can form many designs using the modular tables. And I believe you have an assignment. Can you pass them all to the front? May I ask one volunteer to share his or her assignment to the class? Oh yes, Jel, where's your work?
For this assignment, I I use multiplication modulo 5. Since it is under multiplication, it is expected that the products of the second row and the second columns are zeros. So I just concentrated for this side. To make my design beautiful, I represent each number by certain figures. For number 1, I use orange arrow. For number 2, I use a donut-like figure. For number 3, I use a thin arrow. And for number 4, I use 2 block squares. So, after substituting each number to its corresponding design, I have here now my design. This design is obtained from translation. The next design,
Maybe we can post it here.
the next design is obtained by reflection. And the last design is obtained by rotation. So these 3 designs are obtained using the multiplication modulo 5, and that's my work.
All right, let's give her a big round of applause. So she was able to produce 3 different designs. Are they all different? The last 2 look the same to me. Did you make a mistake, Jel? Wait. Take a closer look at this. If you look at this closely, you can really see that this side was reflected on this side. And if you notice the arrows here, they went around. So that's the main difference. Actually, Jel was able to produce 3 different designs using the table for multiplication modulo 5. So now you can start looking around, and see if some objects follow these modular designs. What could these objects be? They could be the wrappers that we use to wrap our gifts, and they could be the clothes that we wear. Sometimes they really follow modular designs. I believe some cloths woven by the ethnic groups like the Tinalak, they follow modular arithmetic. It's basically translation. And I think the batik follows the rotational design, and some others use reflection. Okay. Wanna make more designs?
Yes.
Okay, but let's take a look at the table first. Let's review. We have here addition table modulo 12. Last time, when we discussed associativity, commutativity, identity, and inverse, I heard somebody mentioning the word group. Who was it? I think he was trying to relate it to his lesson in another subject, which is abstract algebra. Yes, is that correct? Okay. Our set Z12 together with the operation addition modulo 12 forms a group. Why? Because we're talking about a non-empty set, right? So it has the elements 0 to 11. And we are talking also about a binary operation. Remember, we only add 2 elements at a time. And is our binary operation closed? Meaning, if you add any 2 are the sums part of the set, look at this one. Are all the entries here part of the set that contains 0 to 11?
Yes.
Okay, so our operation here is closed. And we have discovered that it is associative and an identity element exists. What was the identity that we found out? What's the identity? Okay, 0 is the identity element. And did each of the element have an inverse?
Yes.
Okay, therefore, this is a group. It's actually a commutative group. Okay. The question now is Z12 under multiplication modulo 12 also a group? Let's see. This is the table for multiplication modulo 12. Let's check if the properties exist also. Is it commutative? Is it commutative? How do we check for commutativity again? We take any 2 arbitrary elements. So A and B, so is A times B equal to B times A? Actually, there's a simpler way for checking whether a table is commutative or not. What do we need to do? All we need to do is highlight the diagonals and check if the entries are symmetric with respect to this diagonal. Take a look at this. This is 6 times 4. Is it equal to 4 times 6? They're both 0. And notice the cells, they are symmetric with respect to the diagonal. How about another pair? This is 11 times 2. Is it equal to 2 times 11?
Yes.
Okay, are they symmetric with respect to the diagonal?
Yes.
Actually, for all pairs of elements in the set, you will find that they are symmetric with respect to this diagonal. So this table exhibits commutativity. How about associativity? Is this table associative? Can you give me 3 values from the table? 3 values? 3 elements. Give me 3 elements. Anyone? Yes, Kimberly?
2, 8, and 10.
Okay, let's see. Is 2 times the quantity 8 times 10 equal to the quantity 2 times 8 times 10? Okay, let's see. On the left side, what is 8 times 10? From the table, you get 8. All right. And what is 2 times 8? You'll get 4. Will we get 4 on the other side also? Let's see. What's 2 times 8 from the table? 4. And what is 4 times 10? 4. So, this particular set exhibits associativity. Actually, since this is finite, you can check for each possible group of elements, and you'll find that Z12 is also associative with respect to multiplication modulo 12. Identity. Do you think an identity element exists for this particular set? If 0 is the identity element for Z12 in addition modulo 12, what do you think is the identity element for addition, for multiplication modulo 12?
It's 1.
Any guess? Is it 1? Let's see. Yes. So from the table, you get the same number when you multiply by 1. Okay? So, the identity exists. How about an inverse? Does each of the element have an inverse? Let's see. What's the inverse of 0? In other words, what will you multiply to 0 to get a 1? None. So 0 doesn't have an inverse. How about 1? What's the inverse of 1? 1. Okay, because 1 times 1 is equal to 1. How about 2? Does 2 have an inverse? Will you get a 1 in this row? No. How about 3? Does 3 have an inverse? Will you get a 1 in this row? No. 4? No. Actually, the only elements that have an inverse are these 4. Okay. 1, 5, 7, and 11. So, is this a group? No. It may be commutative, but it's not a group. Okay. So, actually, if we generalize that, Zn with addition modulo n is a group, but Zn under multiplication modulo n does not form a group. Okay? Now, let's make some designs. We'll be making 2 sets of designs, one for addition and another one for multiplication. All right. Do you remember how to construct your addition table? All right. There's an easy way to construct addition tables. So if we talk about Z5, what would our elements be? 0, 1, 2, 3, 4. So this is addition modulo 5. 0, 1, 2, 3, and 4. Alright, so 0 added to this will give you the same set of numbers. If you add 1, you start with 1. You'll get 2, 3, 4. What's next? Do you see a pattern on how to construct the table? Yes, you start here with 2, 3, 4, 0, 1. Here?
4, 0, 1, 2, 3.
All right. Now let's make circular graphs. Since we are talking about Z5, our modulus is 5. Let's concentrate on this. On this addend. 1. So we have 5, so I have to mark 5 points here. This would be 0, 1, 2, 3, 4. All right. Look at this table. I connect 0 to 1. 0 to 1. Next, I connect 1 to 2. 1 to 2. Next, 2 will be connected to 3. 3 will be connected to 4. And 4 will be connected to 0. So what figure will I form? Okay, it's actually a pentagon. All right. What figure will I get if I use 2 now? Any guess? What would my graph look like this time? So this is 0, 1, 2, 3, and 4. So our modulus is 5, our addend is 2. So we will concentrate on this portion of the table. So to whom shall I connect 0? Okay, 0 will be connected to 2, and then 1 will be connected to 3, and then 2 will be connected to 4, and then 3 will be connected to 0. What do you think will be formed? 4 will be connected to 1. So this is the graph for 5, 2. Okay? All right. Actually, there's a simpler way of doing that. Let me show you another table. This is addition table modulo 7. All right. Let's do 7, 1. So I have to mark 7 points. 0, 1, 2, 3, 4, 5, 6. So to whom shall I connect 0? Okay. So we're doing 7, 1. Actually, all I need to do is to add 1. So if I start from 0, what is 0 plus 1? Okay. What is 1 plus 1? What is 2 plus 2? What is 3 plus... that's 2 plus 1. Sorry. What's 3 plus 1? 4. 4 plus 1? 5. 5 plus 1? 6. And 6 plus 1? 0. Okay. That will be the graph for 7, 1. Okay. How about for 7, 2? So again, we mark off 7 points. 1, 2, 3. Let this be 0, 1, 2, 3, 4, 5, 6. So if this is 7, 2, all I need to do is to add 2. So if I start with 0, I'll just count 1, 2, connect. Here, I'll count 2. 1, 2, connect. Count 2, 1, 2, connect. 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 So this will be our graph for 7, 2. Now, are you ready to make your own graphs?
Yes.
All right. So you work in pairs or threes. I'll be giving you sets of papers to work on. Wow, look at those graphs. Okay. Do you see some patterns? Let's start with the first columns. Actually, the first and the last graphs. What do you notice about the first and the last graphs for each set? Yes? There, Ronnie?
The first and the last graph are the same.
Okay, so let's make some conjectures. First conjecture, the first and the last graphs are all the same. So if we generalize that, and what will be our addend? For the first graph, it's always 1. Okay, n1 is equal to n. Okay, n minus 1. And their graphs would look like, what can you say about their graphs? This looks like a triangle, a square, a pentagon. So they look like, yes, polygons. Convex polygons. Actually, if you have placed the points equally spaced around the circle, you form regular polygons. Okay, so this is actually convex polygons of side what? Okay, that's correct, side n. Very interesting. How about other observations? What can you say about 5-2 and 5-3? 6-2 and 6-4. Here, 10-2 and 10-8, all right? 10-6 and 10-4. Here, 11-3 and 11-8. All right. Here, 12-9 and 12-3. What do you notice? They're all the same. So can you make a generalization? Another conjecture? And yes, if we want it to be k, this will be equal to which one? N, yes, the modulus is still n, and the addend is n minus k. All right. What else do you notice? Any other observations? Look at the green ones. The middle portions of the green ones. What can you say about the green ones? The green ones are the 4, 6, 8, 10, and 12. So if our n is even, what can you say about n, the middle ones? 4, 2, 6, 3, 8, 4, what's next? 10, 5, and 12, 6. What can you say about the graph? Okay, the addend is n over 2. And how do the graphs look like? They look like a pizza. Okay, they're actually a set of, what do you call these lines? Intersecting lines. Well, we're talking about circles. So what part of circles? Okay, they look like a set of diameters. Okay. Other observations? Other observations. When do you get picked stars? Picked stars? Picked. Those that you can construct without lifting your pen? Were there graphs that you were able to construct without lifting your pen? No? Continuously from 0 ending in 0 also? Which are those? Which are those?
If n is odd.
Is it when n is odd? Which ones are those? Let's see. Who did 7-2? 7-2 was done continuously without lifting the pen. Okay. And so was 7-3. 7-2, 7-3, and of course 7-4 because these two are equivalent, and 7-5 as well because it's equivalent to 7-2. When do we get picked stars? Is this a picked star? No, you didn't draw them continuously. 8-3 was done continuously, and so it was 8-5. Here, which ones were done continuously? 9-2, 9-4, and of course their partners 9-5 and 9-7. Here, which were done continuously? This one, 10-3, and the partner 10-7. How about 11? Yes, 11-2 and the partner, 11-3 and the partner, 11-4 and the partner, 11-5 and the partner. So can you make any generalizations? What can you say about this number here and this number here? Does it have something to do with odd and even?
Yes.
Huh? Let's see. We have 9-2, 8-3, 9-5. 9-2 was done without lifting the pen. 9 is odd, 2 is even. 8-3 was done without lifting the pen as well. But 8 is even and 3 is odd. I don't think it has something to do with odd and even.
Relatively right.
Yes, Ronnie?
The graph would be a picked star whenever the n and its addends are relatively prime.
And the addend here. For example, let's denote it by D. Okay.
When n and d are relatively prime.
N and D are relatively prime. Meaning, they're relatively prime. So, since this is smaller, does this divide the modulus? No. Okay. So, our D, if D does not divide the modulus, right? We get picked stars. Okay. And any more observations? Any more observations? What if D divides the modulus? For example, we have 8-2 here. Our D divides the modulus. Here, 3 divides 9. What do we get? Here, 3 divides 12 and 4 divides 12. What do we get? Let me highlight it first. So when we did 9-3, we were able to form this. That would be 1. This would be another 1. And this would be another 1. So how many figures, how many distinct figures were used? So we were able to get 3 polygons, right? 3 polygons of side. What's the side 3? Because they are triangles. All right. How about in, where? 10-2. Okay, 10-2. 10-2, how many figures, independent figures were used? This one. Oh, where is it? Here. That's the first one. And here's another one. So we were able to form 2 polygons of side 5 each. How about here in 12-4? Okay, you were saying 4. May I ask Migs to highlight the 4 polygons that can be formed? Okay, that's 1. That's 2. Red again. 3. And, 3. 4. Where's the 4th one?
The red one.
Hmm?
The red one.
The red one. Okay, so we were able to produce 4 polygons, each of side 3. Okay, so how do we generalize that? If D divides N, what do you form? The graph would have how many polygons? D polygons of side N over D, N divided by D each. Okay? Does that cover everything? D divides N. If D divides N, 4 divides 8. Will you get D polygons of side N over 2 each? No. So what's wrong with our generalization? There must be a restriction. Except when? Okay, except when N over D. So if D divides N and N over D is not equal to 2. I'm sorry, let's change that. N over D is not equal to 2. Right? Actually, you can find more interesting patterns and you can make your own conjectures and eventually prove them. Okay? What's interesting to note is that when we talk about multiplication, we don't follow the same patterns. So let's have an example. We will use the brackets this time to denote multiplication. So if I have 10, 5, that means I'm working on Z10 and 5 is my factor. So it's not the addend anymore. So I'll be needing this. But before that, let's construct the multiplication.